Hi everyone, this is the first page of the homework assignment that I'm going to upload, and I'll explain what this is showing. I'll start with its middle part right here. We're imagining that this box is one population of people, and this other box is another population of people. Let's actually pretend that they're two different universities, and you're interested in whether the mean height of this university is different than the mean height of this university. And let's also pretend that the mean height of this university is 65 inches. That's the population mean. So the mean height of all students at University 1 is 65 inches. Let's also imagine that the mean height of this other university is also 65 inches. So the mean height of all students at the second university is 65 inches. So the two universities really have the same mean height. And you as a researcher don't know what these population means equal, but you're interested in whether the mean height of one university is different than the mean height of the other university. And to investigate that, you're going to take a sample of students from the first university and record their heights. You're going to also take a sample of people from the second university and record their heights. And on this first page, you're going to take a sample of 5 people from the first university and a sample of 5 people from the second university. 5 and 5, so you'll have 10 total people. You're going to record the heights of those 10 people. And I'm going to have you simulate a study where you actually get an outcome. But first I'm going to show you some other things that I want you to do. So I want you to fill in these two numbers here. I want you to fill them both in with 65, like I did here, to show that the means are both 65. Once you do this, I want you to put 5 here and 5 here, like I did, to show that the two sample sizes are 5. Next, I want you to decide whether the null hypothesis is true. So whether the null hypothesis is true if the population means are equal. You as a researcher don't know what the population means are, but if they are equal, then the null hypothesis is true. So since they are at equal, the null is true. So you would say HO is true. I want you to circle this right here, and also circle that the two population means are equal. So if HO is true, then that means that this is true. The population means are equal. Now we'll have you go down here and mark off the critical values. To be able to find out what the critical values are, we have to go to a t-table. So I can put a t-table online, but if we go to Google right here, we can type in t-table, and it's this one we saw in class. You're going to be doing a 2-sample t-test, and in a 2-sample t-test, the df, the row number in the table, is the total sample size minus 2. So you're taking a sample of 5 people from the first university and a sample of 5 people from the second university, so you have 10 total participants. 10 minus 2 is 8. So you're going to be going to row 8 since you have a total sample size of 10. And we're going to be going to 2 tails 0.05 as our column. So we have to go where that meets up with row 8. And we can see that that the critical value is 2.306. It's where this 8 and this 0.05 meet up. So down here, I'll have you label that this critical value is 2.306. I'll have you put that number in there. and I'll have you put in the opposite critical value, which is the negative critical value, right above where it says CD right here. And it's just the opposite of the number from the table. It's negative 0.306. And I'll also have you calculate some p-values of some t-scores. So with a p-value calculator. So what I want you to do first is to calculate the p-value of the positive critical value and the negative critical value. You can do that on this website right here. Under Google, type in you type p-value calculator into Google. And it's this first one that says p-value calculator under GraphPad. You go to p from t. We have to enter in our critical value, which is 2.306, and our df, which is in this two-sample t-test. It's the total sample size minus 2, which is 8. It's the same number we used from the critical value table. Compute p. Click on compute p, and it'll tell you what the p-value is. The critical value has a p-value of 0.05. It just works out that way. So we know that this one is 0.05. So under here, I'm going to have you put in p equals 0.05 under this critical value right here. And if we entered the negative critical value into the p-value calculator, it would also come out to 0.05. We don't even have to do it because we know it'll come out to 0.05. And I'm going to explain what this p-value means. So I want you to make a dotted line right here. It doesn't have to be in blue, but just make a dotted line like I am. And I'm going to tell you what this p-value means. It actually means that the t-score, well, it tells you what the probability is of the t-score reaching this area in here, starting at the dotted line. Meaning, it tells you the probability of the t-score reaching this critical value and landing somewhere in this area right here. So the probability of the t-score landing in this area right here, in this tail, is actually half of the p-value. So if you divide 0.05 by 2, it's 0.025. So I want you to say 0.025 probability like this. And the probability of the t-score landing in this area, in this tail, is also 0.025. It's also because 0.05 divided by 2 is 0.025. And what this probability actually means is that the t-score will land in here 2.5% of the time. So if you multiply this probability right here by 100, you'll get the percentage of the time that the t-score will land in there. So 0.025 multiplied by 100, and you get 2.5. So the t-score will land in here 2.5% of the time. And if you multiply this by 100, it also comes out to 2.5, so it's 2.5% of the time. So what this means is that the t-score will reach this negative critical value and land somewhere in this tail 2.5% of the time. The t-score will reach a positive critical value and land somewhere in this tail 2.5% of the time. What I want you to do next is to pick some number that's lower than the critical value. You can, I'll use 1.7. I just want you to use a number that's a little bit different than 1.7, but it can be close. Like you could use 1.6 or 1.8 if you want to. But whichever number you pick, put the opposite right here. And then go to the p-value calculator and enter in your new number. So I picked 1.7, so I would say 1.7. My DF hasn't changed, so I'll put 8. It's a total sample size minus 2. And I actually got 0.1276. So this t-score has a p-value of 0.1276. So under here I'll put p equals 0.12. It's fine if you round it off to 2 decimal places. So here it's also 0.12. Well, I actually entered 1.7 when I did it, and it gave me and it told me that the t-score of 1.7 has a p-value of 0.12. But if I entered in negative 1.7, it would also come out to 0.12 because a t-score and its opposite always have the same p-value. So if 1.7 is 0.12, I already know that negative 1.7 is 0.12. So pick the number that you're going to put here, and then calculate its p-value like I did, and then put the opposite of your t-score right here like I did, and then put the same p-value under here like I did. Next, I want you to make another dotted line right here, and another and a dotted line above the opposite, and then tell me the probability of this t-score being reached. We already know that what the probability of this t-score being reached is, and this one right here, we know that this one has a 0.025 chance of being reached, and this one has a 0.025 chance of being reached. But what we need to know what the probability of this t-score being reached is. To be able to find it, you actually have to divide the p-value by 2. So 0.12 this is from the calculator. If I divide 0.12 by 2, it's 0.06. So this t-score of 1.7 has a 0.06 probability. It's just 0.12 divided by 2, it's 0.6. Now I have to multiply 0.06 by 100. And it comes out to 6, which tells me that this t-score will be reached 6% of the time. And since this is just the opposite of that t-score, it's going to be the same. 0.12 divided by 2 is 0.06. So make an arrow right here and say that this also has a 0.06 probability. And a 0.06 probability, this t-score has a 0.06 probability of being reached, and it will be reached 6% of the time. Now, lastly, what I wanted you to do is to pick some number beyond the critical value out here. Maybe you could pick, well, I want you to pick a number other than what I did, but I'm going with 2.7. You could just pick something around 2.7 or around that, whichever number you want. Maybe you could pick 2.8 or 2.9 if you want. And I also want you to put the opposite here. So whatever number you decided to put here, put its opposite right there. Then I want you to take your number here, your new t-score, and calculate its p-value. So I went with 2.7. So I'm going to enter in 2.7 and the df of 8. The df is still 8. It's the total sample size minus 2. My new t-score has a p-value of 0.02, or it actually rounds up to 0.03, so I'll say 0.03. So 2.7, the t-score of 2.7 has a p-value of 0.03. And if that's true, then the opposite of that t-score, which is negative 2.7, has the same p-value. So this is also 0.03. So this t-score of 2.7 has a 0.03 chance of being reached, and this t-score of negative 2.7 also has a 0.03 chance of being reached. So I'll have you put another dotted line here. So basically every possible t-score on the number line has its own p-value, because every possible t-score has its own probability of being reached. Now I'll have you and there's actually one other thing I want you to add in here that I didn't put yet. See where I said 0.025 probability and 2.5% of the time? I need you to add in something here that says when H0 is true. So it's actually this t-score has a 0.025 probability of being reached when HO is true, and it's also reached 2.5% of the time when HO is true. And this is also when HO is true. This t-score will be reached 2.5% of the time when HO, and has a 0.025 probability of being reached when HO is true. So under all of these, put when HO is true. And we can do it one more time right here. These two t-scores, 2.7 and negative 2.7, had a p-value of 0.03. And that means that if we divide 0.03 by 2, this is 0.015 probability. And if you multiply that by 0.015 by 100, comes out to 1.5% of the time. But we have to say when HO is true. So the t-score will reach 2.7 or higher 1.5% of the time when HO is true, meaning it has a 0.015 probability of reaching this small tail when HO is true, and it'll land in this small tail 1.5% of the time when HO is true. And if we divide this 0.03 by 2, we get the same thing. 0.03 divided by 2 is 0.015 probability. If you multiply that by 100, it's 1.5% of the time. When HO is true. So basically, the t-score will reach this number and land somewhere in this tail 1.5% of the time when HO is true, and it'll reach this t-score of negative 2.7 and land somewhere in this tail 1.5% of the time when HO is true. Okay, so this finishes this part of the work I wanted you to do down here, and now I wanted you to actually do some simulations, or to actually simulate your own study. So we need to go to that t-score simulation website. So this is the website. So this says treatment and control, but this is actually the two universities that you're studying, University 1 and University 2. You have to enter in what the mean heights of the universities are. So enter in 65 and 65, because those were the population means that we're working with right here. Yeah, because I said that there's 65 and 65. So it's like we're creating two universities that both have a mean of height of 65 inches, and we can actually sample those universities. So I said to take a sample of 5, and you're also taking a sample of 5 from this one. Click on Simulate. So here, I'm sorry. The standard deviations can be whatever we want them to be, but let's just use 5 and 5 for this assignment. So 5 inches and 5 inches. This is mean. This number stands for how spread out the population numbers are from this average. Let's just say 5, and let's simulate. So these are both 5, these are both 5. This, 66. Well, the 5 people from this university had a mean height of 66. That's their sample mean. The 5 people from this university had a mean height of 63. That's their sample mean. So this sample mean overestimated the population mean by a little bit. This sample mean underestimated the population mean by a little bit. What I want you to do is, well, first, is go to this other sheet that I'm giving you, and under HO is true, put your first outcome. It's a mean of 66.74. For sample 1. It's fine if you want to round it off to 1 decimal place, so I'll just say 66.7. And you need to put the mean of sample 2 from the second university, which was 63.78. Or you could round it to 63.8. I want you to also get the sample mean difference, the difference between the two sample means. You can get that by subtracting this sample mean by that sample mean. So it's 66.7 minus 63.8 comes out to 2.9. I also want you to put the t-score. So let's see what the t-score was. Yours was, or the one I got was 0.86. So if the first sample mean is higher than the second sample mean, like it is here, the t-score is positive. So it's positive 0.86. So I'll put 0.86 here for t. And for p, what I wanted you to do is to actually tell me what the p-value of this t-score would be. More specifically, what we need to do is we need to find out if this t-score would have a p-value less than 0.05, and I'll show you how we can find out. So first, once you have all of this, what I want you to do is to put the first sample mean of 66.7 right here. This is the first mean. This is the mean of the first sample from University 1. I'll have you call it X bar number 1. We also need to put the other sample mean, the mean of the first sample from University 2. So let's see what that was. It was about 63.7. So that should go about right here. I want you to also call it X bar 1 because it's the mean of the first sample from the second university. So this is the mean of the first sample from this university. This is the mean of the first sample from this other university. I want you to plot the sample mean difference, which we found out was 2.9, positive 2.9. So it would go out here. And then I'll have some tick marks here for you. And then I want you to put the t-score down here. So the t-score was 0.86. 0.86. So just put it right here in between these 2 points, the letter T. So what we've done is we've plotted the first sample mean, or the mean of sample 1, the mean of the other sample, sample 2, the sample mean difference, and the t-score. And since this t-score of 0.86 that we found in our study is below the critical value, it didn't reach the critical value right here, it has to have a p-value above 0.05, because all t-scores that fall short of the critical value down here have p-values above 0.05. So all I really want you to do is to say that p is above 0.05. And when I say decision, I want you to make a decision about the null hypothesis, which means, well, we know that the null is true because the two universities that we're sampling have the same population mean, but you as a researcher wouldn't know that, and you would have to make a decision. So since your t-score landed in this middle area between the two critical values in here, you would fail to reject the null hypothesis, because this area between the critical values is called the non-rejection region. So you would say fail to reject HO under here, or you could just say fail. And where it says error, I want you to tell me if you made a correct decision or not. So you failing to reject the null means giving the null the benefit of the doubt, and in this situation, that's the right decision because the two universities you're sampling do have the same population mean. So under here, you would just say correct decision. And then what I wanted you to do is to imagine that the study that you just did is being repeated. Either you're repeating it or someone else is repeating the study. So the study is being repeated, so 5 other people are being selected from University 1, 5 other people are being selected from University 2, and from the same 2 universities, and their heights of the 10 people are being recorded again. So either you or someone else is trying to repeat the study. Click on Simulate again, and you'll get new results. This time, these 5 people from University 1 have a mean height of 67, and these 5 people from University 2 have a mean height of 63. So once again, it looks like this overestimated a little bit, this underestimated a little bit, but it's still close. So 67 and 67.7 and 65.8. This time the sample mean difference will be, well, it's whatever we get when we subtract these 2 numbers. So +1.9 because the first sample mean is bigger. Then the t-score would be whatever it came out to right here. It comes out to 0.597. So we'll put 0.59 right here. Then what we'll do is we have to decide what we have to say what the p-value of this t-score is. This t-score has been found in the second study. We have to see what p-value it has. So what we really just care about is if the p-value is under 0.05. So this was 0.86. This other t-score would be a little bit lower. So maybe this one would be here. This one would be right here. Like that. And then 0.5. This is the first one and the second one. So this one also, this new t-score of 0.5 or 0.58, I think, is also below the critical value, which means that the p-value has to be above 0.05 because when you go from 0 up further away from 0, the p-value is getting lower and lower. And at this point, at the critical value, it drops to 0.05, and everything past has a p-value under 0.05. So this one has to be above 0.05. So you would say that its p-value is above 0.05. You can probably already tell that if the p-value is above 0.05, it means that the critical value was not reached. So we fail to reject because it's not in the rejection region. It's also a correct decision again because the null really is true. So I'll have you keep repeating this. So each time you do this, put these in here. I also want you to keep plotting them up in here. So I forgot to plot these. So for the second outcome, the first sample mean is 67.7, which is it's about the same. So if they're really close, you could just stack it like above because they're about the same number. And this other one, the second sample, number 2, came out to 65.7. So that's actually up here. Because the first time we got a number down here. So this is what this 2 means is it's the mean of the second sample from University 1. This is the mean of the second sample from University 2. So you have to put the 2 sample means, then the new sample mean difference. So this time it came out to the new sample mean difference I think was 1.9. It was a little bit smaller than last time. Yeah, positive 1.9. So maybe that right there. Because last time I think it was about 2.9 maybe. So the sample means weren't quite as far apart this time. And I actually want you to label these ones also. So since how I said 1 and 2 and 1 and 2, I also want you to put these as 1 and 2. And also T1 and T2. Like this. So the first time, the first simulation gave us 1. So everything that says 1 was from the first simulation. 1, 1, 1. And this T-score right here. Everything from the second simulation is here. 2, 2, 2, and 2. And we'll just keep, I want you to just keep repeating that. And each time you do a simulation, plot these in here like we did. And also go here and fill in all of this. And if you ever get a T-score that does reach the critical value out here in this simulation, when you're simulating from these 2 populations right here that are actually equal, you're simulating and the HO is true right here, and the T-score does land out here, you would end up rejecting the null hypothesis. So that would be, you would put everything here like before. Sample mean 1, sample mean 2, the difference, the T. But if you landed in the rejection region, then your T-score actually has a p-value under 0.05. Because remember, all T-scores that are in the rejection region past the critical value have p-values under 0.05. We saw that earlier on. And it would be reject would be your decision, reject the null. And well, in this situation, a rejection would actually be a mistake. If you reject the null and it's actually true, it's a type 1 error. And you can just go through some of these simulations here. Once you get finished with those, what I want you to do is do some simulations over here. So once you've finished all of this right here, I want you to in other words, once you've done these here, these simulations with the null hypothesis being true, and you've also plotted all of your work, all of your outcomes, sample mean 1, sample mean 2, the difference, and the t for each of your simulations. Once you get finished with all of this, I want you to move on to this other simulation over here. I want you to do 65. So what we're imagining now is that these are two other universities. They're not the same two universities over here. This university has a mean height of 65 inches, and this other university has a mean height of 75 inches. And I want you to enter in these two numbers. I still want you to use a sample of 5 and a sample of 5. This time, you would circle each one is true, and you would circle that the first population mean is higher than the second population mean because they're different. So now you're imagining that you're a researcher who's actually studying these two populations. You're interested in whether the mean height of this university is different than the mean height of this university. And unknown to you, the two universities do have different mean heights, which is why H1 is true. If the population means are different, H1 is true. This time, I don't want you to do all of this work down here with the p-values and all of this labeling, because all of these probabilities that we're talking about only apply to this situation when the population means are equal. When the population means are equal, and you're sampling from those two populations, then these are the probabilities of all of the t-scores in that situation. If the population means are actually different, like they are here, those probabilities don't apply, so you don't have to do that. So I still want you to put the critical values. So this would be it's still the sample size hasn't changed, so the critical values are still the same. It's still 2.306 and negative 2.306 for the two critical values. So this time, I want you to switch the simulation and change it to 65 and 75. Keep everything else the same. So now you're taking 5 from here and 5 from here again. This time, this sample mean is pretty close to this population mean, and the sample mean is pretty close to this population mean, which is what we would expect. And because of that, the sample means are much further apart, which gives us a bigger t-score. So I want you to go over here where each one is true, where we're in this situation, and type in, because this is the situation in which this population mean is lower than this one. So your first simulation is 62.8 for the first sample mean. It's 73.8 for the second one. And for a difference, you have to subtract the first one by the second one. The difference is negative 11, which is a pretty big difference between sample means. So when if this population mean is 65, all of these sample means, or most of these sample means, should be near 65. If this population mean is 75, most of these sample means should be near 75, which means that usually this sample mean is going to be lower than this sample mean because, well, if this population mean is higher than this population mean, this sample mean will usually be lower than this sample mean. Put the t-score. This time it's negative 3.5. So we're having a bigger t-score. The t-score is going to usually be negative because, like I said, this sample mean is usually lower than this sample mean in this situation, which means that if sample mean 1 is lower than sample mean 2, the difference is negative, and t is also negative. So let's plot this for your first simulation. Plot 62.8. It's about right here. That's x bar 1. 73.8 is about up here. Sorry. It's about here. T is, it's actually, remember it's a negative number, because if sample mean 1 is lower than sample mean 2, it's a negative t-score. So if it's a negative 3.5, which is about down here, it's in the negative rejection region because it's past the negative critical value out here. Because this is critical, that's critical. So if it's in this area out here, it's reject HO. Well, first, if it's in the rejection region, if it reached the critical value, P is below 0.05, and the decision is to reject. And if H1 is true, then rejecting the null is correct. If you reject HO, that's the right decision. So it's actually a correct decision because we're rejecting HO in favor of H1, and that's the right decision about the populations. Next, we would do another simulation. So this time we got 64.6, and this one, so here we have something interesting. So this came out to 64.6. This one underestimated the population mean by quite a bit, by chance. So our sample means didn't come out as far apart as they usually would. We got 64.6 and 69.9. The t-score was 1.88. Actually, negative 1.88 because this is lower than this. You can say, sorry, that's actually the t. The sample mean difference would be this minus this, which would be, I think, negative 5.3, which isn't as big of a difference. So here, we need to plot our outcomes. So 62.8 that's about at the same place. 69.9 is actually way out here. The difference is about, we forgot to plot our first difference, which would have been, I forget what it was. Oh, it's negative 11, which was out here. So I should have put this out here as the first difference of negative 11. Our new difference is negative 5.3, which is maybe right there for sample mean difference. So we plotted the two sample means and the sample mean difference. We need to plot the new t-score, negative 0.888. That's actually, well, I should have put a 1 here. That's only about there. It's in the non-rejection region, which means it's in between the critical values, so it's telling us to fail to reject the null. So we would go here. If it's in between the critical values, p is actually above 0.05, like it was over here when it in the other situation. Which would mean actually fail to reject the null. A researcher who got this outcome would actually fail to reject the null, and it would be wrong because they're giving the null the benefit of the doubt, and H1 really is true. So it's actually a type 2 error. If you fail and H1 is true, it's a type 2 error. So you can keep doing this for these outcomes. So you'll be just filling these in with each simulation, and you'll also be filling in each time the first sample mean, the second sample mean, the sample mean difference, and the t-score. Yeah, the first sample mean, the second sample mean, the sample mean difference goes here, and the t-score goes on here somewhere. Once you finish these, I want you to do one more set of simulations. Right here. Now create a situation where you're studying two universities, and this university has a mean height of 75, and the second one has a lower mean height of only 65 inches. So this university is taller than this university. You're still taking a sample of 5 from here, and a sample of 5 from here. So now you would go to your simulations and change this to 75, change this to 65, keep the standard deviations the same. You're using the same sample sizes. So now it's going to be 72, which is near this population mean, and 63, which is near this population mean. So now the first sample mean is higher than the second sample mean. So I'll put 72.6 is my first simulation over here. And the other one, 63.6. For each of your simulations, I want you to calculate the sample mean difference, which right here would be 72.6 minus 63.6 equals 9 exactly. It's actually positive 9. We have a positive sample mean difference because this is higher than this, which means we also have a positive t-score, 2.05. Now we need to plot our outcomes here. So the first sample mean was 72.6. That's x bar 1. The second sample mean was 63.6. That's a little bit lower, so it's down here. It's still 1. The sample mean difference was 9, positive 9, so it's out here somewhere. So we'll put x bar 1 for sample. It's actually a sample mean difference of plus 9 out here. And since the sample mean difference is far above 0 and positive, the t-score is going to be pretty far above 0. So once again, I need you to label the critical values, which haven't changed. It's negative 2.306 and plus 2.306. This is all you have to do. This work is only for the middle one. What did it come out to? 2.05. That's a little bit short of the critical value. It's in here, so it's actually in the non-rejection region between the critical values. The sample means weren't far enough apart for t to be out here in the rejection region, which means we're not convinced enough to reject the null. Since it's in the non-rejection region, p is actually above 0.05, because that's, if it's in the non-rejection, it's above 0.05, which means that the decision is to fail. And once again, if you fail to reject HO, if you fail and H1 is true, it's a type 2 error. So you'll continue with these. Couple more things. Up here, I wanted you to actually put what the population means are. So here, put 65. Here, put 75. So you can actually compare the population means to the sample means. Here, put 65 and 65. Here, put 75 and 65. And then one last thing I wanted you to do is under here, put, well, underneath each of these number lines for sample mean 1 and sample mean 2, put mu under here to show that this is the mean of this population. Put mu under here. That's the mean of the other population. Do the same thing here. And put this mu here. And put this other mu right there. One final thing is I want you to label this as a t-distribution, because what actually happens when the null is true and the study is repeated over and over in this middle situation, all of the different t-scores that are found pile up to form a shape called a t-distribution, because the t-scores pile up near zero most of the time and don't pile up out here as often. So the p-values actually come from the shape of the t-distribution, because out here they only happen 5% of the time, out here they only happen 3% of the time. Same thing here. They start to happen only 12% of the time, only 5% of the time out here, and only 3% of the time out here. In this middle situation. Out here, you're probably going to see something different where they're much more likely to pile up at the negative end. And out here, you'll see that they're much more likely to pile up at the positive end. So these percentages don't apply to those other two situations. These are only when the null is true.